Hi, everybody. This is your Unit 6 review video. Now, there are going to be no questions on this one. I just want to go through and briefly touch on all of the topics that we talked about in this very, very long unit. I think we've been on here a whole 6 weeks. So let's go ahead and just review. That way you have, all of this information in one spot before you take your Unit 6 mastery, okay? So we started the unit by talking about physical changes and chemical changes. Remember, physical changes alter like a physical property, but not the chemical composition. And a chemical change is an actual chemical reaction, right? Where we have chemicals that are changing their composition throughout. So some of those physical properties here, things like color, scent, the state of matter, and chemical properties are things like flammability, toxicity, and stuff like that. So we can see some of these physical changes: melting an ice cube, boiling water, breaking glass. We're not changing the chemical composition there, but something like rusting or burning or cooking or a battery, that is a chemical change, right? And so some signs of a chemical change are color change, the formation of a solid, formation of a gas, light being produced, a change in odor or scent, and then burning and a change in temperature. Okay, and we talked about our chemical reactions. And so they're set up. We have the reactants, those produce the products. And so that's split by the yield sign. So we have reactants on the left, products on the right. We're going to kind of switch that up a little bit in the next unit when we talk about equilibrium, but it's always going to be reactants on the left, products on the right. Okay. And so then we got into talking about counting atoms, right? Remember, your formula for counting atoms is simply just coefficient times subscript, okay? So you can see here what we did with H2O was we took the coefficient of 2, multiplied by each subscript. So 2 times 2 gives us 4 hydrogens, and 2 times 1 gives us 2 oxygens, right? If we don't see a number there, we assume it is 1. That goes for subscript and coefficient. And we did a ton of practice on this. You can go back and watch that video specifically on me to go through all these problems for you, but same kind of thing here. 2 times 2 gives us 4 iron atoms or Fe atoms, and 2 times 3 gives us 6 oxygen atoms here, okay? Then we moved into the 5 types of reactions. We have synthesis reactions. That is when 2 or more reactants combine to form one more complex product, or A plus B yields AB. And so you have an example of that here with chlorine and sodium. Um, then we have a decomposition reaction, which is the opposite of that, right? If synthesis is two simpler things becoming one more complex thing, decomposition is one more complex reactant breaking apart to form 2 or more products that are simpler, okay? And that would be AB yields A plus B. Then we have our single replacement reactions, where we have one element that replaces another ion in an equation or in a compound. And so that would be a metal replacing a metal ion, or a non-metal replacing a non-metal ion. And that's what happens here, right? So it's like the dance partners cutting in, kind of analogy here. And we also said that we haven't talked about this a ton. We just want you to know that not all single replacement reactions happen, right? Something has to be higher up on this reactivity series than what it's replacing for that reaction to happen. Okay. Double replacement, it's just where you have two couples that are dancing and partners just switch, right? So you just have metal ions switch places with each other, and you get two new compounds that are formed in that reaction. Okay, and then finally, you have combustion reactions where we have a hydrocarbon and oxygen gas giving us carbon dioxide and water. Okay, and so those are our 5 types of reactions, and then we talked about Antoine Lavoisier and how he gave us what we call the law of conservation of mass or matter, and that says that matter cannot be created or destroyed, only rearranged in chemical reactions to form different compounds and substances. Okay, and this is why we must balance our chemical equations. Right, we need to have the same number of atoms of each element on both sides of the equation. We can't show that we are creating or breaking something, and the way we do this is we use the box method, right? So we kind of visualize this by putting a box around each compound, and then when we do our initial count of our substances, we look at how we can add elements to each side. We have to add a whole box. So on the right side here, if we need to add more chlorines, we have to add a whole box of NaCl. And so that means we have to add more Na to the other side. And so that's just kind of a game of push and pull, of balancing out each of the elements in here, right? And we do that by tracking this underneath the yield sign there. We've had tons of practice on that, and then we got to our first mastery, where you needed to label some things, answer some questions, and do your paragraph, your claim on whether or not the student balanced the equation correctly and why. Okay, and then we got into the mole. So the mole was our way to give a number to a very, very, very large number that's hard for us to conceptualize, right? So just like a dozen is 12, a mole is 6.02 times 10 to the 23rd of something, right? So when we say we have 1 mole of water, what we're meaning is that we have 6.02 times 10 to the 23rd molecules of water, okay? And we learned that we can relate that to mass. And so if we have 1 mole of water, we're also going to have 18 grams of water, right? Because that is a molar mass. It's the number of, it's the amount of mass in 1 mole of a substance. And so we did that when we find molar mass of things, we just use the chemical formula and we multiply the number of moles by the mass from the periodic table, and then we just add them up, right? So here we had Li3N, lithium nitride, so we did 3 times lithium's mass of 6.941, and then added that to 1 times nitrogen's mass of 14.007 to give us a total of 34.83 grams per mole, okay? And so then we said, we can actually convert between moles and mass, right? So we can, if we're given, like, we need 6 moles of this for a reaction to go forward, we can use the molar mass to help calculate how many grams of something we would need in order to get 6 moles. And then we can also, if we're given, hey, we're producing 7 moles of water in this combustion reaction, how many moles of a hydrocarbon did we use? We can see with our mole ratio right here that we use the balanced chemical equation to figure that out. All right, we have videos on all of those. I'm not going to go through the actual math in that here. I just wanted you to kind of remember that we had all that stuff. Okay, and so that is where our unit ended. We ended with the brief mass to moles and moles to moles problems. So we are going to have a 20 question quizzes over this unit. It will encompass everything that we just talked about right there. You can take it as many times as you'd like. The goal here is for you to be successful. So please take it and take it and take it and take it until you do well on it. And we will be starting our next unit next week, where we talk about chemical reaction rates, and we'll be talking about things like exothermic and endothermic and how energy moves in and out. And so we'll be taking what we're learning here and stepping it up 1 notch to make it a little more complicated for us. Okay, so thank you. Let me know if you need help, and good luck on your mastery.